Lost in low Earth orbit. From this altitude, help feels close. Every 90 minutes, you complete another orbit. Ground control knows exactly where you are. But knowing doesn't mean reaching. If your suit is breached, you have seconds. Air rushes from your lungs, not because it's sucked out, but because the pressure difference is so extreme your body can't hold it in. 10 seconds, unconsciousness. 90 seconds, irreversible brain damage. If your suit holds, you have hours instead of seconds, but the outcome doesn't change. Your spacesuit carries enough oxygen for 6 to 8 hours. It regulates pressure, controls temperature, scrubs CO2 from your breath. What it cannot do is change your velocity. You're still moving at 7.8 kilometers per second, with no engine, no thrusters, and no way to slow down. By the time any spacecraft could launch, match your orbit, and reach you, you'd be 3 hours past dead. Then there's the debris. More than 30,000 tracked objects share this orbital space, each one moving fast enough that a paint fleck hits with the force of a bullet. One impact, that's all it takes. In low Earth orbit, your suit doesn't save you. It just gives you time to understand what's happening. Lost near a space station. This is the scenario that feels survivable. You can see the station. You're close enough to make out individual modules, but you're moving away at 0.3 meters per second. Slower than walking, faster than rescue. The problem isn't distance, it's orbital mechanics. The moment you separate, your trajectory diverges. The station completes an orbit every 90 minutes. You complete yours in a slightly different time. Each orbit, the gap widens. Ground control would need to assess the situation, prepare another astronaut, depressurize the airlock, and launch a pursuit, all while both of you are moving at 28,000 kilometers per hour in slightly different directions. The maneuvering jets on your suit? They're designed for fine adjustments during spacewalks, not pursuit across orbital paths. You'd run out of fuel in minutes. Near a space station, you don't die from distance. You die because motion, once changed, cannot be undone, and time runs faster than help can arrive. Lost between Earth and the Moon. The distance between Earth and the Moon is 384,000 kilometers of mostly nothing. No stable gravity, no atmosphere, no radiation shielding. If you're lost here, you're not orbiting anything. You're just moving. And without propulsion, you'll keep moving on whatever path you're already on. Earth's gravity still pulls, but weakly. Falling back would take days, and only if your trajectory is nearly perfect. A small error, and you miss Earth entirely. Your suit now faces extremes it wasn't designed for. In direct sunlight, 120 degrees Celsius. In Earth's shadow, minus 100 degrees Celsius. Without active rotation or shade, you'll either cook or freeze. Whichever happens first depends on where you're pointed. The oxygen still runs out in 6 to 8 hours. But now, radiation becomes the slow killer. Outside Earth's magnetic field, you're absorbing 2 to 3 times the dose of low orbit. Every hour, more cellular damage. No shielding, no repair. Between Earth and the Moon, death doesn't arrive suddenly. It accumulates degree by degree, dose by dose, until your body crosses a threshold it can't return from. When life support becomes a countdown, let's assume the best case. No debris strike, suit intact, oxygen flowing. You've survived every immediate threat. You're still dying, just slower. Modern spacesuits are engineered for hours, not days. Oxygen reserves, 6 to 8 hours. Carbon dioxide scrubbers, strict limits. When CO2 rises above 2%, breathing becomes labored. At 5%, confusion sets in. Beyond that, your body loses the ability to regulate itself. Temperature control relies on evaporation and radiators. Without controlled orientation, heat doesn't shed efficiently. Internal temps begin climbing, even in the freezing vacuum of space. Then there's your body. In microgravity, fluids shift toward your head. Pressure builds inside your skull. Vision blurs. Headaches intensify. Your cardiovascular system, evolved for Earth's gravity, starts working incorrectly. Radiation continues damaging cells every minute, every hour. None of this fails dramatically. Life support doesn't collapse all at once. It degrades quietly, incrementally, until one system tips past the point your body can compensate. In space, staying alive isn't about having air. It's about how long your systems can maintain balance before time tips them into failure. Lost on the way to Mars. Mars is, on average, 225 million kilometers from Earth. The journey takes 6 to 9 months. If you become separated during this transfer, every problem you've already encountered still applies, but now, the scale breaks comprehension. There's no gravity well to fall into, no orbital loop to predict, no interception possible. You're traveling too fast, too far for anything to catch you. Your suit's oxygen, still 6 to 8 hours. Communication delay to Earth, 4 to 24 minutes, depending on planetary positions. By the time Earth receives your distress signal, your oxygen is already gone. By the time they could respond, you'd been dead for hours. Radiation exposure on a Mars transfer, zero point 0.6 to zero point 0.7 sieverts over the journey, hundreds of times Earth surface levels. With no magnetic field for protection, cellular damage accumulates continuously. Between Earth and the Moon, space removes options. On the way to Mars, it removes distance, time, and the very concept of rescue. Locked into a fatal trajectory. Now imagine the nightmare scenario. Your suit works perfectly. Oxygen recycles, temperature holds stable. You have food, water, and radiation shielding beyond anything we've built. You're still doomed. Because you're moving. Everything in the solar system is already in motion. Earth orbits the Sun at 107,000 kilometers per hour. Jupiter moves at 47,000 kilometers per hour. If your trajectory bends even slightly toward a massive object, gravity doesn't pull you in suddenly. It commits you quietly. At first, nothing feels different. Acceleration, 0.5 meters per second, you wouldn't notice. But weeks pass, your velocity climbs. There's no friction to slow you down, no propulsion to cancel the motion. The environment changes faster than your systems can adapt. Radiation rises, magnetic fields intensify, particle impacts increase as your speed climbs. Eventually, velocity itself becomes lethal. You're striking even sparse particles with explosive energy. If your destination is a planet or the Sun, the final limit arrives quickly. Gravity-driven acceleration overwhelms structural limits. Thermal loads exceed any control system. The critical moment isn't when you arrive, and it's when your path becomes irreversible. From that point on, your life support doesn't fail. It simply stops mattering. At the end, there's no explosion. Earth becomes a point of light. Your radio crackles with messages you'll never answer. System indicators continue their rhythms. Oxygen, temperature, heartbeat, all functioning normally. Nothing dramatic happens. You simply keep moving, long after survival stopped being possible. Like and subscribe for more scenarios. Drop a comment. Which death scenario should we cover next?